What's going on, smart people? Today we are picking up our conversation with a bunch of nuclear physicists, and I put out a post in my community tab asking you to leave some questions you have regarding nuclear physics, and that's what we're going to be going through today. So without any further ado, let's just get into it. Cool, so again I am joined with Filip, Jingyi, Daniel, Astrid, and Caleb. Unfortunately, Aaron from the last video wasn't able to make it, so we're just going to have to try to make do without him. Thanks again, everyone, for joining me today. So I have a bunch of questions from people who watch the videos who have some questions for us all about nuclear physics, and I just figured we could kind of just go through them and have a little bit of a conversation on all of these questions that people have. We're not going to get through all of them, just kind of the top ones. Sound good, everybody?
Excellent.
Awesome.
Sounds good to me. Good.
So I'm going to go ahead and start sharing now. So over in my community tab, I said we're doing a video with a bunch of other grad students in the HUGS program. That's before I had the idea to invite the postdocs as well, which Astrid is. They're going to ask some questions about research, grad school, and let's go ahead and just start reading through some of these questions. So the top one, actually YouTube categorizes this stuff weird. It's sorted by top, but it's not really sorted by top. But in any case, the first one says, are national labs like Argonne a good fit for theorists, and how likely is it to get into one?
I can step in. So colleagues of mine and me, we applied for a position at Argonne, and it's very suitable for theorists, and I have many colleagues who are actually at Argonne. So just because it's a lab, it doesn't mean that it's not inviting for theorists, much to the contrary. So I'm a theorist now at Jefferson Lab, and it's very inviting, at least for theorists doing phenomenology, meaning that you're closely working together also with experimental data, doing things that are interesting for the experiment or that experimentalists hope to use models for. And they have a very big theory department, a very strong one in nuclear physics in Argonne, and also Jefferson Lab where I am. So definitely it's suitable and existing for theorists.
Cool. As someone who's still in undergrad, by the way, if anyone has stuff to say, I'm just in read mode, but if you have something to say, just speak up. So as someone who's still in undergrad, I feel like I've had much more exposure to particle physics than nuclear physics. From my limited knowledge of the two subjects, they seem very similar. Two questions. Are nuclear and particle physics as similar as they seem? And what made you choose nuclear over particle physics? Okay.
Yeah, that's a really good question, and maybe I can say something about that. So you're definitely right that there's a lot of overlap with nuclear and particle physics. Of course, we know that the nucleus is made up of particles, and the fundamental theories of particle physics are exactly the same as the fundamental theories of nuclear physics. So there's a huge amount of overlap, and even those of us who are in this nuclear physics program, many of us do consider ourselves to be particle physicists. I certainly think of myself as a particles guy who just applies it in sort of a nuclear direction. So yeah, there's huge overlap, and certainly if somebody's talking about particle physics, plenty of those same techniques, topics, and things occur as well in the nuclear domain.
If you think about it, 2/3 of the interactions in particle physics are nuclear reactions, like the strong and weak nuclear forces, and you probe the nature of them through the electromagnetic interactions typically, right? So it's like, yeah, that overlap. Maybe it's more of a historical difference at this point. I'm not too sure.
I think I can also have a few comments as an experimentalist, because I think in the sense of the experiment, the major difference is the energy scale. So, and the energy scale actually decide the scale of the experiment. So for high energy physics, we always have a huge lab and we have a huge accelerator to achieve a significant high energy. But for nuclear physics, relatively, we will have a smaller lab. In this case, as an experimentalist, you will have more chance to get in touch with every aspect of the experiment. For example, I can participate in the construction of the experimental setup, but I think in a high energy facility like LHC, if I do data analysis, I will never have a chance to get into the aspect of how do we set up the experiments, because most of the setup is already fixed.
That's a really good point.
Can I answer the second part of that question?
Sure.
So what made me choose nuclear over particle? For me, it was where I could find the most interesting math to do. And I think that's largely up to the advisor that you work with, because one advisor might make you do nothing but programming to fit some model to data. Another one might make you calculate next to next to next to leading order Feynman diagrams. Or yet another advisor might say, okay, I have this whole new branch of mathematics I invented to study this problem. And I try to go in that direction. And that happened to be in a nuclear direction.
Okay, so the next one, computing question. So what kind of computational or high-performance computing problems do we face during research, and what resources and techniques do we use? So anyone particularly computation-heavy in their research?
I'm very interested. I think that question is very interesting, so I would like to say a few words. So I think from all perspectives, so both experimentalists who have to handle huge amounts of data, they have heavy computation to do, and theorists as well, for several reasons. So they can range from pure theory, meaning you need to really numerically compute really difficult equations or integrals or something, so you just need something that has power for that, or more or less theory heavy but more analysis heavy. Let's say we have the world of machine learning coming up, which we are also applying onto many of our theory models now. And there, of course, as with any AI, you just need a lot of computational power. And you also have the world of lattice QCD, where you need very strong computing resources to actually get formalism to describe the world as closely as possible to the real world. And for that, so the computational resources usually mean, both for experimentalists and for theorists, they mean that you have really strong computational clusters, usually on site if it's national labs. So most of the national labs I'm aware of, they have their own computing clusters there. And you rarely use your personal computer anymore for heavy computing. You're really just doing this centrally. So it's always good to just have a joint cluster where everyone just runs the codes there, because everything that needs to be installed is already installed there because one person uses it at some point, so everyone else after that can use it as well. So that's my 2 cents.
Do any of you have to worry about like parallelization and things like that? My stuff is all just Mathematica or relatively simple Python scripts. The only thing that I run into is how can I speed up the way that my code does this numerical integration. That's 99% of my coding endeavors.
Yeah, mine is basically the same as yours. I have stuff written on Mathematica, and I don't really care about how slow it takes as long as it gets done within like a couple of hours. So I just let it run in the background and not worry about it too much. But yeah, I know that others have much more complex data sets and calculations to do. So I'm really the wrong person also to speak about this topic.
So, in my research, I have to run some simulation to simulate the reactions when the particle interact with the detectors. And so by running this, because we are trying to study, for example, the background for the experiment, that we have to achieve enough statistics. So in this case, we have to actually run a large amount of data. And normally we will run it parallelly using the farm at JLab. I think one issue we have to think about is how do we allocate the runtime of each of the program or each of the job. Because if the job runs too long, it will be killed. And if the job runs too slow, actually we have to spend more time waiting for our job to be run. So this is one of the issues we have to think about.
Absolutely. Daniel, were you about to say something as well?
Yeah, so for me personally, I need to do fits. So I've got some theory that is coded up and needs to be fit to data. And so I throw my theory at JLab's computers, and then people smarter than me make sure that all of that stuff works, and it takes several million computing hours, but then fits pop out. But I've also had friends in the past who simulated like the thermalization of quarks into a QGP after a proton-proton collision, and that required GPU computing. And down the hall from me, people are doing relativistic hydrodynamics, and that also requires GPU computing.
This one question has to do with the Madala boson. I don't really know anything about that. Can anyone speak on?
Yeah, so my understanding from the very brief, 10 minutes I spent reading one paper, is that what people are essentially proposing is that we have the standard model that explains all the visible matter that we have. But we also have, suggested that there's a new type of particle called dark matter. And maybe that has its own sort of copy or version of the standard model for how all these dark particles interact with each other. And the only way that we can measure dark matter is through gravity. So we know that because the Higgs gives particles their mass, which we know interacts gravitationally, that means there must be something that connects our standard model to the dark standard model. And so it seems to me that my understanding of that one paper I read was that the suggestion is that there's a new boson that they call the Madala boson that interacts across these two standard models, essentially. So it interacts with our Higgs and with some kind of equivalent on the dark side as well. So I thought it's a very interesting idea, but of course, right now it's highly speculative, but still very interesting and exciting. I only spent a couple of minutes. I really didn't do it justice. So I apologize also to the person who asked the question. I don't know enough about this to really say more.
It sounded good to me.
Yep.
So the next question was, how far is nuclear physics understood and how much research is still made and has to be done? So how far along are we?
I like to think of this as a race. We've gone like 100 miles in this race. The problem is we don't know how long the race is. It could be 200 miles, it could be 500 miles. So it's an interesting question, but until we know how much nuclear physics is, and in which case we'll probably be done, we won't probably be able to say how far we are in physics until we're done.
And we're kind of in a sweet spot, right? We know a lot already indeed, and we still know that there are a lot of open questions at the same time. So it's like we achieved a ton, and still it's not like we're out of our jobs, because even the things that we know, so the miles that we see in front of us, although we don't know where the end of the race is, we still see there's a lot of miles in front of us. So there's a lot of stuff to do. I think that's a really nice spot to be in.
Yeah, I think maybe I could say something maybe a little bit longer about this as well, because I like to think about things by taking sort of a step back and looking at the bigger picture. So our goal with physics and with any science is, of course, to come up with a theory that explains all experimental data. So we have over here, you first come up with a theory, and then from that theory, you extract a prediction. Then you do an experiment and see, does the experimental value agree with the predicted value? If yes, then you say, okay, this experiment supports the theory. And then over time, you keep extracting more and more predictions from the theory, keep testing them one by one, and eventually you build up a confidence or a non-confidence in that theory. So how that applies to nuclear physics is, our theory for that is called quantum chromodynamics, or QCD for short. Every prediction that we've ever been able to extract from the theory has been agreed by experiment. The difficulty we have is not in coming up with the theory and not in coming up with experiments. The real difficulty we have is that at low energy, it's very difficult to extract predictions from the theory. So we understand nuclear physics quite well at high energy, where it's relatively easy to extract predictions and they keep agreeing with our experiments. But at low energy, there are certain techniques that you can do, but we really don't have a very good theoretical handle on exactly how to get good predictions out of the theory.
Perfect.
Yeah, I don't know. Maybe that's a more sort of complete answer. I don't know.
Yeah, it's like, oh, we're done. We have the equation. We just don't know how to solve it all the time.
Exactly, precisely.
Just to bring it into the context of the summer school that we just finished. So something we have a good picture of is like the hydrogen atom and how the electron moves around it, and we can picture it and plot it and even directly observe it with the right tools. But we don't know, or we're not able to do the same thing for the inside of the proton. We know it's made up of these quarks and gluons, but we don't quite know how they arrange themselves. But right now, we're starting to build up all of the theoretical and experimental tools that we need to properly image the proton. And so within the next 10, 20 years, that is one major question that we should be able to answer. Like, what is the 3D structure of the proton?
Okay, sorry about that. Do you want to start? Do you mind starting over?
You're absolutely good. I can start over, yes. So I think it depends very much on whether the CV is meant for academia or for a company. So of course, company application should be much shorter and just have the absolute highlights in it. However, I think for both it applies that you shouldn't have any gaps in the CV. However, how you fill them is of course a little bit up to you. I think if the CV is not very long yet, so let's say you're in the middle of graduate school or at the end and you're applying for a first postdoc or so, likely you don't have that many conferences or papers to show yet. So it's good to just list them all. At some point, maybe if you have a lot of teaching experience already, you don't want to list every single class that you ever gave. You can just say teaching experience from 2010 to 2020 and put some highlights in there, like tutoring, like heavy advanced quantum mechanics or something like that. And at the same time, gave some piano classes or so if you want to show some versatility or something like this. So I think it's absolutely okay, as Philip said, to be a bit more minimalistic, even on the academia CV side, as long as you put the highlights in. And for example, if you have many publications and you would like to stress that you have many publications, you don't have to list all your 100 publications, let's say, but you can say, I have 102 publications with 2 citations. The highlights are these top 5, which I'm really proud of, and I did the main work for, or something like this. So I think it's fine to, depending on how much experience you have, if you feel like it's a huge list of things, to just start folding them together.
Awesome. I think you can speak on that behalf better than all of us, so I'm glad that you had something to say about it.
I would advise having a full CV with everything you've done, so that when you want to apply for some position, that you can then cut out stuff that you don't think is necessary for it. But I think it's good to have a CV with all the stuff you've done, just so that you have it somewhere, so you don't have to try and rack your brain next time you're trying to figure out, next time you're applying to a job and you're trying to figure out what you did and what might apply to it. So
that's a good point. I think I'm going to pick and choose some, not all of the questions from this, just so that we can get to other people as well. So I see one that I think is kind of interesting. How do you know which equations to use in your work? Do you look at an experimental problem first and try to model the data, or do you investigate the boundaries of a theory?
For me, it's the second case. You look at the theory you have and say, where does this apply? How can I apply this in a new way? As you say, at some boundary of the theory. But usually, there are practical questions as well. And like, will this, this boundary, will this be relevant to the data that we have? So there's a lot of thought that goes into it. I'm sure that some people do try to just straight up model data and try to figure out what kind of function could this be. But at the end of the day, no, most theory people really are doing, as you said in the second part, investigating boundaries of the theory, where it's applicable and how you can extend it.
Yeah, I guess one summary that one of my old professors said, he said, theory guides, experiment decides. So I don't know if there would always be the experimental data in the region that's interesting unless the theory said to look in that regime in the first place. So, but I don't know if it's like how useful it is if it's ad hoc, if it's always like, I want to explain this data specifically.
Exactly. So just because, you have some plot of the data and you say, I'm just going to fit a polynomial to this, that's not really that useful to anybody. We need to know more information.
And as for the experiments going after theory, sometimes it's also a matter of, that's why you get proposals through, right? So experiments usually mean more money investment than theory needs, because we need pen, paper, and maybe expensive computers. But usually for at least nuclear physics and particle physics, you need very expensive experiments. So if you want to have a proposal for them, actually go through and convince a committee to pay you for it, usually it's because there is already some theoretical foundation saying it might be good to look in that particular place. However, that theory might be not very developed yet, and it will be more developed once data is there. So it also goes in the other direction, right?
So I think I'll do one more question from this person, then we'll move on to a couple more from other people. This one's about grad school interviews and what kinds of questions you were asked.
You guys were interviewed?
Yeah, I don't recall.
I only
grad
had one
school.
school that didn't interview. The rest of mine didn't do interviews at all.
I had one that interviewed me, yeah. So in my experience, it was like the stuff that I put in my personal statement was what they focused on. So if I said that, I think I said that I enjoyed computation a lot, and I think at one point I was like, it doesn't really matter too much what I'm doing. I just enjoy, solving problems numerically. And so they were like really probing that. What kind of computation do I like? What language do I use? Would I be interested in this branch of physics? Yeah, that was my very minimal experience.
Yeah, my experience was slightly different because I applied to a bunch of different grad schools, but I only got accepted to places that either already knew me personally or that somebody had reached out to a specific person to look out for my application. So by the time that I had an interview for my grad school, the person I spoke to in the interview already knew me. We'd already met once face to face and had a long discussion. So he basically just sat there and said, this interview is just to make sure you're not some crazy person. And that was that. So everybody's experience will differ, of course.
Well, my interview was actually very different because physics is my second major. So at that time, they want to know what did I learn and how deep did I learn in physics. I got two interviews. One is from Duke University. So basically, the director at that time asked me everything about quantum physics, step math. I think everything I have learned.
Oh God.
Yeah, when I prepare, I look at some experience online, and most of the people tells you that in most of the interview, they will only ask what is your interest and what is mostly they are the research related problem, right? But for me, it is actually very hardcore.
Yeah, that sounds
terrifying.
That's exactly what I was going to say.
Yeah.
Maybe, but for the person who's asking, maybe there are forums or something for the grad schools that you're considering where students are sharing their experiences. Because when I was applying to grad school, those things are everywhere, where people are talking about specific universities. Or maybe you can reach out to like their GSO, their grad student organization, and see if anyone can shed some light on what the interviews for that school covered. Because just from us three, like the results may vary, I guess. This one looks a little tough. Is there any way we can meaningfully carry out fusion, nuclear fusion on Earth, like what goes on in the core of the sun?
Well, the way it works in the sun is that there's lots of gravity crushing all of the hydrogen together. So we can't do it exactly like in the sun.
Yeah, right. Nobody's figured out a way yet, but if we've learned anything from the progress of science, it's to never say never. Most likely in 100 years or so, at least, this something like that will be possible.
I think the common answer is we're always 20 years away from nuclear fusion. Isn't that what it is?
Yes, I recently had that conversation also. Yep. No matter when you ask, it's always 20 years.
Okay, I think I want to save this one. This one will probably be the last question. Oh, Astrid, this sounds up your alley. What's the future prospect for someone interested in applying machine learning algorithms in nuclear physics?
Okay, I have to be careful what I say here then. So, as a disclaimer, machine learning is extremely powerful already for, say, our day-to-day life things like, as you know, face recognition and even recognizing traffic for automatic driving and so on. So that's things where it can readily be applied and it has achieved a lot. For the projects I'm involved in, we're at the moment bringing machine learning to speed to actually be able to reproduce what data we already have. So basically if we feed it some basic knowledge, we want it to give us back what experiment also gave us back. So it's still at the stage where it's actually very close to it. So basically you could just throw away your data storage and just press OK on your machine learning device, and it will just create new storage for you. So that's nice. So that's good for data maintenance, let's say, or for keeping it, even if it's like huge amounts of data, if you can just recreate it again without needing to run the experiment again. So it's more or less there. It's not better yet. So what machine learning is extremely good at is interpolation. So say you know one point in space and another point in space, and it will guess what is in between. So for example, if you have some green here and some green there, it will guess there's more green in between, so it won't just plug a smiley face into it. What it's not so good at is extrapolation, meaning it knows what is in this image here, but it doesn't know what is outside. So you don't know that next to me there are two bears, for example, which I didn't tell you all this time. So hey, bears. So that's something that machine learning will not achieve that soon, let's say it at least. So it's not there yet for new physics, let's say, but it's extremely good already at reproducing what we already have.
Okay, let's do a little bit of a speed round real quick. So these next ones will be not very comprehensive, but just to get a couple more in. So someone's asking about quantum numbers, and we have one for strangeness, but not other quark numbers like charge or charm. And why is that? Well, that's not true. If you look in like the particle data group booklet, and you look at like the meson summary table, there's charmed, strange, mesons, and it gives you the quantum numbers for those as well. Maybe strangeness is quoted more just because that was the first one that was outside of up and down.
So it's more historical than anything else.
I think we actually answered this one in the last video, or rather Jingyi did, about what's going on with the proton size problem. Do you wanna give a quick elevator pitch to what's going on in the world of how big is the proton?
So there are still a lot of ongoing experiments so far. For example, one in Jefferson Lab and the other called Muse, I think in Europe. So basically, there are still a lot we can do. For example, trying to minimize the uncertainties in the experiment and trying to really compare apple to apple by using different experimental techniques. So I think one word I can say is that we still have a lot to do, and there are also a lot of meaningful progress so far.
Apparently this person put something in twice, probably on the video and then here, and said just to make sure it's in the Q&A. So I guess we'll probably end off with this one. I did not quite get the relevance of the deeply virtual Compton scattering. I understand it's the simplest process related to generalized parton distributions, but what exactly can we learn from it? And is it related to the Compton wavelength or the Compton effect? I'll just speak on that real quick. So what you can learn from it, well, like you pointed out, it gives you access to generalized parton distributions, and under certain limits you can relate these to very physically intuitive things, like parton distributions, like how the quarks and the gluons are distributed spatially inside of the proton, or how are their momentum distributed. You can also gain access to things like how is mass distributed, angular momentum. So there's a lot. It's very rich, full of physical quantities with that. Okay, last one, and then because I forgot that I said that we'd do this one. What is the next big thing to discover in nuclear physics?
Is the color glass condensate real?
That might be the biggest thing for you and me. I'm not sure if it's the same for everybody else though.
It seems like I think we all agree on like big problems in nuclear physics, like how is spin divided up inside of the proton and neutron. That's always a big question that we're interested in. And how is everything else distributed? This is stuff that we're just now starting to get a handle on how to not only ask that question, but where is the answer? What kind of objects, mathematical objects, is that information contained? Okay, well, I think might as well wrap it up here. I appreciate you all taking the time to do this with me. I know we just finished the Hugs program, like less than half an hour before we started this video, so I'm sure everyone's tired. But thanks again for doing this. For people whose questions weren't answered, I'll probably go through and maybe type some stuff up by hand, and obviously you all feel free to do the same if you like. But yeah, thanks again. I hope everyone, I hope you all had a fun time participating in the video. I hope you watched and enjoyed watching it. Let me know in the comment section if you did, and I'll see you guys there.